Okay, everybody, how's it going? Connecting to you from the lumberyard this time. It's a little chilly outside, but all right. What we intend on doing today is continuing with the examples, but this time doing a complex valued problem and showing how that translates into the solution and all that sort of fun stuff. Okay, so if we start, what I'm going to do is I'm going to start this time with the differential equation. So x prime equals x plus y over 2, and y prime equals negative x. And so from here, you want to be able to extract the coefficient matrix A. So what's in front of the x here is a 1. What's in front of that y is a 1/2. What's in front of the x here is a negative 1. What's in front of the y there is a 0. There's my coefficient matrix. Cool. All right. The first step here that we need to do is we need to calculate the eigenvalues. Okay. And so I think a quick and dirty way to do that would be we can compute the trace, which, like we had said before, is the sum along the diagonal. So 1 plus 0 is 1. And we can compute the determinant, which is the product of those guys in green minus the product of these guys in orange. So 1 times 0 is 0, minus negative 1/2 is 1/2. And so this means my eigenvalues are lambda equals the trace plus or minus the square root of the trace squared minus 4 times the determinant, and all that over 2. And so what we get here is 1/2 plus or minus 1/2 I. So they're complex value. Awesome. We should already know that this is going to be a hassle. Okay? But what's nice about complex, because they're always come in conjugate pairs, like this, where the front part, the alpha, is always the same and the beta is always the same, we're only going to have to work with one of them. All right, so the one I'm going to work with is, I'm just going to go ahead with the plus sign. So 1/2 plus 1/2 I. All right, now if we plug that into the matrix as follows. So we need to calculate A minus lambda times the identity matrix. And so that's going to be 1 minus lambda, 1/2, negative 1, negative lambda. Yeah, I do it different every time just to kind of show the different ways that we can go about this. Okay, so 1 minus 1/2 leaves us with, whoops, don't scroll. There we go. 1/2 minus 1/2 I. Okay, we just have a 1/2 up there. We just have the negative 1 right here. And then negative my eigenvalue is negative 1/2 minus 1/2 I. So there's my matrix. I'm multiplying this by V1, V2. And this is supposed to equal the 0 matrix. All right. I'm writing large. I'm kind of leaving myself a lot of space. But what we can always do is just basically choose one of these, because they do carry redundant information. So I'm going to use this one. All right, so I'm going to have 1/2 minus 1/2 I, all that times V1, plus 1/2 V2 is supposed to equal 0. And at this point, you might be wondering, like, well, what the heck am I supposed to do? I've got a complex valued thing over here, and I got a real number over here. Well, 0 happens to be the exact same as 0 plus 0 I. All right, so we do indeed have a complex number over here. It's just kind of in a simplified form. Now, what you may be tempted to do, and it's 100% totally understandable, because it's the thing that I would have done first, and it's the thing that really does kind of make sense, is to say, okay, look, I need my complex part over here to equal the complex part over there, and I need everything that's real over here to equal everything that's real over there. All right, and in doing so, what you end up equating is, whoops, negative 1/2 V1 equals 0. And so you would get that V1 equals 0, which may be okay. The problem there, though, is that you would get 1/2 times 0 plus 1/2 V2 equals 0, which would imply V2 equals 0. And this is not good, because the eigenvector 0, 0 contains no information. And in fact, it's counter to what we even want. We wanted to find a solution where my vector was not 0. And the reason why we may get to this point right here is because we are thinking in the real numbers. We're not thinking hard enough, okay? V1 and V2 don't have to be real numbers. So let's erase that stuff. Let's start this investigation all over again. All right, and instead, excuse me, I want to a priori, since I know I can choose one of these to be whatever I want, I'm going to pick the V that's in the most complicated situation and make it the number 1. This right here is a complicated situation, so I'm going to let V1 equal 1. And so then I get 1/2 minus 1/2 I plus 1/2. And now instead of writing V2, I'm going to write, let's go ahead and pick some letters here. Yeah, let's go U1 plus U2I equals 0 plus 0I. Where this right here is V2 just written out with a real part, U1, and a complex part, U2, just in all of its glory. So now I have the following. I have 1/2 plus 1/2 U1. That's my real part. That should all equal 0. And then I have negative 1/2 plus 1/2 U2. And that should equal 0 because that's my complex part. And now I can solve each of these all by themselves. U1 therefore equals negative 1. And U2 therefore equals 1. Is that the eigenvalue I got earlier? It feels wrong. Looks like I got something different earlier. Let's double check my work. Yeah. What did I do over here that was so wrong? Da 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 da. I have 1/2, negative 1/2 I, and then, yeah, that looks absolutely perfect. Oh, because I did it wrong on my piece of paper. Haha. So, anyway, my eigenvector, therefore, for the eigenvalue 1/2 plus 1/2 I, has the eigenvector 1 in the V1 position and negative 1 plus I in the V2 position. So now you may be wondering, sort of like, okay, great, I've got an eigenvalue, which I shouldn't have bothered writing it over there because I'm just going to rewrite it right here. I've got an eigenvalue, which is complex, and I've got an eigenvector, which is also complex. What does this do for me for real solutions? Well, if you remember from before, these guys can be interpreted to help give us solutions. So let's work on all this, okay? So first things first, this gives me a vector valued solution to my problem. And what it is I write my eigenvector down, plus I, and then I've got e to the 1/2 plus 1/2 I t. All right, that looks simple enough. Let's take this vector right here and let's blow it up into its real and complex parts. Okay, so the real value on the top is a 1. The real value on the bottom is a negative 1. Plus I times the complex value on the top is a 0. The complex value on the bottom is a 1. So this is a whole nother way of just rewriting that vector like we had before. And then this, we should remember how to handle it because this is exactly how we got our sines and cosines. We have e to the t over 2 times cosine t over 2 plus I sine t over 2. Now we still have complex values in here. Okay, but let's do just a little bit more work on this thing. What I want to do is I want to write it down as a single vector of just real functions plus I times another vector of complex valued functions, okay? So it's going to get a wee bit ugly. All right, first things first, absolutely everybody's got an e to the t over 2. That much is for certain. Now I'm going to open parenthesis. Now if I look at the cosine part, there's no I on there. Okay, so when I multiply it by this term, actually let me back. I went back too much. All right. If I take this cosine and if I multiply it by this 1 right here, I will get a real valued function. I will get cosine t over 2. If I multiply the cosine by this 0 right here, I get 0, so it doesn't matter, it doesn't contribute anything at all. All right, and then in the bottom, if I take this cosine and I multiply it by this negative 1 right there, I will again get a real valued function, negative cos t over 2. All right, so far so good, right? Now, if I look at this sine function I've got sitting over here, it's got an I in front of it. So only when I multiply it by another I will I actually get a real thing. So if I multiply this, I don't want highlight anymore. If I multiply this guy by this orange term up here, I'll get complex valued. It doesn't belong in this. And if I multiply it by the 0, it's 0, so it doesn't matter. If I multiply it by the negative 1, I'll again get a complex valued function. So that's a problem. But if I multiply that I sine business with this 1 right here, with the I in front of it, those two i's will become a negative 1. And so I can add onto here minus sine t over 2. And that's all the real stuff from this whole big product. And then I can add to this, so plus I times, and now I want all my complex functions, okay? Now, cosine times the 1, that's real. Cosine times the 0, that's 0, doesn't matter. I sine times the 1, hey, that's complex. Sine t over 2. And sine times 0, that's 0, it doesn't matter. Cosine times the I1, hey, that's complex. Cosine t over 2. And then I sine business right here, multiplied by this negative 1, that is again complex, so minus sine t over 2. All right. So now we look at this. It's big, ugly, and I'm in the way. I've got two vectors, one right here and one right here, and I have a complex valued solution. Now we can go through the exact same proofs we did for second order differential equations to show that the real part, which is this one right here, and the complex part, which is this one right here, they are both themselves, all by themselves, actual solutions to the problem. And so what I've got, if I push down one more, is I've got x1, which is a vector valued function, which is equivalent to e to the t over 2 times all those real valued parts in those vectors. Oh, whoops. I think I might have done that wrong. Nope, too far. Right here. No, it's a negative and a negative. Okay. Minus sine t over 2. That's a solution. And we also have e to the t over 2. T over 2 times. I'm trying my best. And then I grab all the folks that are in the complex. So this sine and then this cosine minus sine. So sine t over 2, cosine t over 2 minus sine t over 2. And now I've got two solutions to a two-dimensional problem. So my general solution is C1 times x1 of t plus C2 x2 of t. And that's all there is to it. So this is if I write it in vector form. If I write it in component form, you know, we'd have x equals e to the t over 2 times cosine t over 2 plus sine t over 2. And I made a mistake. There's a C1 there and a C2 in there. Okay. And all this just comes from reading off the top of those vectors. Okay. That's what this is right here. All right. Now my y, again, we're doing component form, right? Is e to the t over 2. And now if I look, I've got a minus, excuse me, minus C1 cosine and a C2 cosine. So I've got C2 minus C1 cosine t over 2. And then I've got a minus c1 and a minus c2. So minus c1 plus c2 sine t over 2. And all that comes from reading the bottom row here. I don't know if you can see that purple. Can you? Oh, yeah, you see the purple. That goes right there. Okay, that's a complex valued one. I really do hope that helps. It's a little hinky, but hey, it is what it is right now. The next video I've got for y'all, if I check real quick here. Oh, okay. We are going to start a great big process of being able to draw those pictures that are in the book of like, hey, what does the phase plane look like? All right. We're going to go through it now that we have motivated why we're looking for straight line solutions. And now that we've done several eigenvalue, eigenvector problems where we see, hey, this is how I calculate those straight lines. We're going to take all this knowledge, kind of squish it all together and apply it to some actual systems and see what we can say basically about the stability of the equilibrium point in these systems, aka the origin. All right, so stick around for another video eventually.